Welcome to this 35-minute overview of compressible flow theory. This presentation is meant for engineering students who have already taken compressible flow in their undergraduate program and are looking for a quick refresher. There will be many important details that are skipped, but hopefully we cover the essentials. This review is going to focus on compressible flow in ducts with an area change. Therefore, I want to start with a brief reminder of how an incompressible flow behaves in a variable area duct. Here we have an incompressible fluid traveling from left to right through a converging section. We want to look at any cross-section along the axis of this converging duct. Realize that everything we're going to look at in this overview is one-dimensional flow. We're not worried about velocity or property profiles across the cross-section of the duct. It's assumed to be uniform flow at any axial location. When we look at the steady-state conservation of mass equation, or continuity equation, we can see that at any axial location, the product of density, velocity, and area has to be equal to a constant. In other words, the mass flow is constant because there's no accumulation of mass in the steady-state case. So we know this equation has to be true. If we differentiate this, we see that we have three terms representing changes in density, area, and velocity. Now remember, we're looking at incompressible flow here, so there are no changes in density. And that leads us to the conclusion that in an incompressible flow, change in area has to have the opposite sign as the change in velocity. Notice, due to this negative sign, dA and dV always have the opposite sign. For a converging section like this, dA is negative, so dV has to be positive, and the flow needs to accelerate in a converging section. Now we're also interested in pressure. If we review the incompressible Bernoulli's equation and realize we're not going to have any significant elevation changes, we can get rid of the potential energy term, and we have pressure plus rho v squared over 2 is a constant. This is conservation of energy. So this is kinetic energy, and the pressure is what's left of the enthalpy term after the other assumptions inherent in the incompressible Bernoulli's equation are made. We see from here that if the velocity goes up, the pressure goes down. This is a result we're hopefully familiar with for an incompressible flow. So decreasing area gives increasing velocity and decreasing pressure in an incompressible flow. Now if that duct goes on to diverge, the velocity will go down and the pressure will go up. As we look at compressible flow, we will see that the behavior of velocity and pressure will be the same, but the behavior of area and velocity will be different. To look at compressible flow, one of the fundamental things we need to consider is the role that the speed of sound plays in the flow of a compressible substance. The first case we will look at is a completely stationary gas. This little dot in the center is a source of noise, a very weak source of noise, so it's emitting acoustic waves. These are very weak sound waves, and they travel radially outward in all directions at the speed of sound. If we say the point is emitting a beep every second, here is the sound it emitted 1 second ago, 2 seconds ago, 3, 4, and 5 seconds ago. Now what is the speed of sound in a gas? We're going to use A as our symbol for the speed of sound. The speed of sound in a perfect gas is the square root of kRt, where K is the ratio of specific heats, R is the specific gas constant as it appears in the ideal gas law, and T is the local temperature. So it's important to realize that the speed of sound depends on the temperature. As the temperature of the gas changes, the local speed of sound also changes. This equation is valid for a perfect gas. A perfect gas is an ideal gas that also has constant specific heats. Everything we're going to do in this overview is for a perfect gas. So that's the case when the velocity of the gas is 0. The next thing we're going to do is have the air start to move from left to right at a velocity equal to 1/2 of the speed of sound. We have our same little fixed emitter of noise, which is beeping every second. The beep that it emitted 1 second ago is there. The beep it emitted 2 seconds ago is there. The beep it emitted 3 seconds ago is there. 4 and 5 seconds ago. The acoustic wave is traveling radially outwards, but the gas is also traveling from left to right, so these circles are no longer concentric. They're getting shifted to the right. Now we want to increase the velocity again. This time we're going to say the velocity equals the speed of sound. The beep that our source emitted 1 second ago is there. Notice that it has shifted to the right the same amount as it has traveled radially outward, so the front edge of the wave is still at the sound source. 2 seconds ago, 3 seconds ago, 4 and 5 seconds ago. Now we see a very different thing happening. We see these waves all piling up at the location of the sound source. This is the beginnings of what we're going to be calling a shock wave later on in this overview. Now we're going to take this even further. We're going to have the velocity of the gas going twice the speed of sound. The sound that this little source emitted 1 second ago, 2, 3, 4, and 5 seconds ago. Now we can join the edges of all these circles with straight lines at both the top and the bottom in this sketch. Assuming that our source is just a point source, in 3 dimensions, that would be a cone. If we happen to be located out here in this region, anywhere outside of that cone, we do not hear that source. Remember, this source is stationary, and if we're stationary, standing out here, and the wind is just blowing by, we will never hear that thing. This is called the zone of silence. If we are located inside the cone, we would certainly hear the sound. This is called the zone of information. In this discussion, we've been presenting velocities as multiples of the speed of sound. However, the speed of the gas is usually expressed in terms of the local speed of sound by an important dimensionless number called the Mach number. The Mach number is the velocity of the gas divided by the local speed of sound. The case where the velocity is 0 gives Mach number equal to 0. When the velocity is half the speed of sound, the Mach number would be 0.5. A gas velocity equal to the speed of sound gives a Mach number equal to 1. If the velocity is twice the speed of sound, the Mach number will be 2. Remember that the Mach number changes from place to place in a flow due to 2 effects: changes in the flow velocity and changes in the local speed of sound. Now I want to talk a little bit about the scope of what we're going to look at in this overview. Any fluid flow can be classified as an external or an internal flow. An external flow would be the flow over top of an airplane wing or something like that. An internal flow is pipe flow or duct flow. It really doesn't matter what the cross-sectional shape of the duct is. We're going to be restricting our discussion to internal flows from now on. There are essentially 3 things that can happen in a duct flow. The area can change, there can be friction on the wall, or there could be heat transfer. There's certainly incompressible flow theory dealing with friction and heat transfer, but in this overview, we are only going to talk about area change. Here we will summarize the assumptions we are going to be making. We're going to look just at steady flow. These are going to be frictionless ducts, although we will relax the frictionless assumption for one special circumstance I will discuss later. There will be no heat transfer, so the ducts are adiabatic. The flow will be one-dimensional, as we discussed earlier. The substance is going to be an ideal gas with constant specific heats. Gravity is going to be neglected. As a consequence of a bunch of these previous assumptions, the flow will usually be isentropic, except for a special circumstance I will discuss later. In a variable area duct, the density, velocity, pressure, and temperature are all changing for a compressible flow. For an incompressible flow, it's only really the velocity and pressure that are changing. To understand the relationships between all these variables, we need a quick review of the governing equations. This is a converging duct. The flow is from left to right. This is a small control volume. We've already looked at conservation of mass. The big difference now is that d rho is not zero. The density will change as we move down the duct. The steady-state energy equation indicates that changes in enthalpy and changes in kinetic energy have to balance. From thermodynamics, we get the second TdS equation, which relates changes in entropy to changes in enthalpy and pressure. Most of what we're going to look at is isentropic, so the change in entropy will be zero. We can combine these two equations together, eliminate the dH, and get a connection between pressure and velocity. The change in pressure, dP, is equal to minus rho v dV. Notice that when the velocity goes up, pressure goes down, and when velocity goes down, pressure goes up, because dP is proportional to negative dV. This is the same behavior as incompressible flow. Now we want to look at the relationship between pressure and area. If we take the relationship between pressure and velocity that we looked at on the last slide and combine it with the continuity equation, we get one of the most important relationships in compressible duct flow, as shown here. This equation relates changes in area, dA, to changes in pressure, dP. The most important feature of this equation is the term in parentheses. This term leads to very different behavior for subsonic and supersonic flows, which we'll summarize in a table. When the Mach number is less than 1, this is a positive number, and when the Mach number is greater than 1, this is a negative number. We'll build a little table to summarize the important implications of this equation. We're going to look at converging and diverging ducts. A converging duct has dA less than 0, and a diverging duct has dA greater than 0. If the Mach number of the flow is less than 1, this is positive. That means dA and dP have the same sign. If A goes down, P goes down, and if A goes up, P goes up. In a diverging duct, since the area is increasing, the pressure is also increasing. Both cases are the same behavior as in compressible flow. Now, if we have a supersonic flow, the Mach number is greater than 1, and this is now negative, and the behavior becomes exactly the opposite. In a converging duct, the pressure increases, which is the opposite of a subsonic flow. In a diverging duct, the pressure decreases. This is a critical feature of compressible flow, and it shows the very important role that Mach number plays in the equations. Now let's say we want to accelerate the flow to supersonic speeds. Here we have two equations we've looked at already. One relates changes in area to changes in pressure, and the other relates changes in pressure to changes in velocity. We can combine these to get one that relates changes in velocity to changes in area. Let's discuss what the duct needs to look like to get a supersonic flow. Here we assume we are starting with a stagnant gas. The way we denote the properties of a stagnant fluid is with a not subscript. Since we are starting with a gas at rest, it certainly begins as a subsonic flow. Therefore, to accelerate the flow, we need a converging duct to begin. Now, as the flow accelerates along the converging section, it approaches Mach number of 1. However, when the Mach number equals 1, this equation tells us that dA must be 0. Further, if we want V to continue to increase, positive dV, we need dA to be positive, since the sign of the m squared minus 1 term will change. This means that to achieve a supersonic flow, the duct area must go through a minimum and then start to increase. Now in practice, the duct wouldn't have corners like this, and there's never a long flat section. We would just have a smooth, converging, diverging section. This location, called the throat, is the only location where the Mach number can equal 1. Now let's look at the case where we only have a converging nozzle attached to a large plenum chamber, where the properties are constant and not affected by the flow out of the nozzle. The pressure in the region the nozzle discharges to will be PB, the back pressure. If PB is equal to P0, there is no flow. Now we're going to reduce this pressure slowly, and the flow out of the nozzle will begin. At the beginning, when PB is still quite close to P0, it's just going to be a subsonic flow. Under these subsonic flow conditions, the pressure at the exit plane, denoted here as PE, will be equal to the back pressure PB, since it is just a subsonic jet. That's going to continue as PB is decreased further until the Mach number at the exit becomes equal to 1. If the ratio of specific heats for the gas is 1.4, which is true for air and any diatomic gas, the ratio of PB to P0 for this condition is 0.528. If we reduce PB further, that change cannot be transmitted upstream past the point where the Mach number equals 1. The flow is said to be choked, and further decreases in PB have no effect on the flow in the nozzle. This will be true even if we reduce PB to 0, a perfect vacuum. Also, the exit pressure no longer equals the back pressure. The maximum mass flow rate through the nozzle will be given by this expression, which depends upon the stagnation pressure and temperature in the plenum chamber, P0 and T0, the specific gas constant R, and the area of the exit, A star. The equations that have been presented so far can be expressed as a set of working equations for compressible flow. The first equation is just the energy equation and gives the ratio of the local static temperature to the stagnation temperature. Working from this equation, and further assuming isentropic flow, we get similar equations for the density and pressure ratios. These three equations give the local static temperature, density, and pressure anywhere along the duct as a function of Mach number. Another important relationship that results is the connection between area and Mach number, where A star is the location where the Mach number equals 1. Notice in a converging diverging nozzle, the expression for the maximum mass flow rate is the same as for the converging nozzle, since nothing that happens in the supersonic diverging section can affect the flow up to the throat. So far, everything we've looked at is for isentropic flow. This will happen if the downstream pressure is sufficiently low. However, if the downstream pressure is not low enough to sustain supersonic flow, a normal shock is going to occur in the duct. It's called a normal shock because it is perpendicular to the flow direction. We have a one-dimensional flow here from left to right. The flow upstream of the normal shock is always supersonic. The converging diverging nozzle we've considered so far will never have a normal shock in the converging section. The flow downstream of a normal shock is always subsonic. Here we're using the subscript 1 to refer to properties upstream of the normal shock, and the subscript 2 to refer to properties downstream of the normal shock. Because we have extremely high gradients of multiple properties inside the normal shock, friction cannot be ignored. Therefore, a normal shock is not an isentropic process, which means the isentropic relationships that we introduced earlier cannot be applied across a normal shock. Now let's summarize other property changes across a normal shock. When you discussed normal shocks in your undergraduate course, you would have developed all these equations. The Mach number goes down across a normal shock, and here's the relationship that we can use to calculate that new Mach number. As with the relationships given earlier, this is based on a ratio of specific heats of 1.4. The velocity goes down across a normal shock as well. The stagnation pressure also goes down. and here it is given as a function of the Mach number upstream of the shock. The static pressure, on the other hand, increases across a normal shock. We have a large increase in pressure across a normal shock, and again, the pressure ratio downstream to upstream is given as a function of the upstream Mach number. The temperature also increases, and there's a relationship for that ratio. Likewise, our last property, the density, also increases across a normal shock. All these property ratios are given as a function of the upstream Mach number. Pressure, temperature, and density all go up across a normal shock, whereas Mach number, velocity, and stagnation pressure go down across a normal shock. Now we will use everything we have talked about so far to summarize the behavior of a compressible flow through a converging, diverging nozzle. The flow originates from the stagnation conditions given by T0, P0, and ρ0. The flow goes through 4 distinct flow regimes as the back pressure PB is reduced from P0 to 0. Note that this represents all relevant values of the back pressure. We have a converging section going to some minimum area, which we call the throat. As PB is first reduced below P0, we get regime 1, where the flow is subsonic throughout the converging diverging nozzle. Eventually we reach Mach 1 at the throat. If we reduce the back pressure further, a normal shock appears at the throat as we enter regime 2. As we continue to reduce PB, the normal shock gets stronger and moves downstream. There would be subsonic flow up to the throat. From the throat to the normal shock would be supersonic flow, and downstream of the normal shock, we would have a subsonic flow again. In regime 3, we have a compression fan outside of the nozzle. At this point, the static pressure at the exit is quite a bit lower than the back pressure. Therefore, as the gas exits the nozzle, its pressure needs to increase in order to get back up to the back pressure. That pressure increase takes place through a complex series of oblique and normal shocks called a compression fan occurring outside the nozzle. The fourth regime is when the back pressure has been reduced so that there is an expansion fan outside of the nozzle. Now the pressure is lower outside of the nozzle than it is at the exit, so as the gas leaves the nozzle, it's going to expand into the surroundings. Now we'll demonstrate each of these 4 regimes with an online calculator that solves the equations that we've been talking about and shows the profiles of the properties through a converging diverging section. There's a link to this calculator in the description for this video if you want to visit it and play around with it on your own. First, let's provide a quick orientation to the simulator. There are only 2 things you can change, the area ratio and the back pressure ratio, and I'll talk about those in more detail later. This just shows the nozzle profile. The flow here is from left to right. This is the exit region. The plenum chamber would be over here on the left. Next is a plot of the 3 main properties, temperature, density, and pressure as a function of location through the nozzle. The last thing it shows is a profile of the Mach number along the axis of the duct. We're starting off at the default conditions. In this tool, we can change the area ratio if we want. This area ratio is the area of the exit divided by the area of the throat. This is an axisymmetric nozzle geometry, so we're looking at the diameter of the throat here and the diameter of the exit here. The default area ratio is 2, and I'm just going to go back to that default. We're more interested in the effective back pressure ratio. This input allows us to change the ratio of the back pressure to the plenum chamber pressure. That's the pressure in the region where the nozzle is discharging, divided by the pressure in the plenum chamber. By default, it starts off at 0.75, which, for this area ratio, happens to be in regime 2. We want to start with a pressure ratio of 1, which means the back pressure is equal to the plenum chamber pressure. This condition gives no flow. The property ratios are 1 all the way through the nozzle, and the Mach number is 0 all the way through the nozzle. Next, we slightly reduce the back pressure down to 0.95. We're told here we're in regime 1, and we have subsonic flow throughout the nozzle. If we look at our property ratios, we see they are near 1 at the entrance to the nozzle, and temperature, density, and pressure all reduce as the flow accelerates to the throat. In the diverging section, they all increase again. This is an entirely subsonic flow. The pressure reduces and then increases again in the diverging section. If we look at our Mach number profile, we see the Mach number increasing to a maximum at the throat, and then decreasing to a Mach number of 0.27 at the exit. Notice that the Mach number at the throat does not reach 1 for this back pressure. The next thing we're going to do is jump to the boundary between regimes 1 and 2. This just sets the back pressure to whatever value is required to match the boundary between regimes 1 and 2. Now we have Mach 1 at the throat, but in the diverging section, downstream of the throat, the flow slows down again so it stays subsonic. The pressure, temperature, and density all recover through the diverging section. The flow is completely subsonic, but just on the verge of becoming supersonic. If we reduce the back pressure any more, we'll start to see at least a portion of the nozzle have a supersonic flow. The next pressure ratio I'm going to put in is 0.8. Now you see we're in regime 2, and we have a normal shock in the diverging section. If we look at the Mach number profile, we have Mach 1 at the throat. The Mach number increases to a supersonic value past the throat, and then drops from a supersonic value down to a subsonic value across the normal shock. We have subsonic flow up to the throat, supersonic flow from the throat to the normal shock, and then subsonic flow downstream of the shock. Now, downstream of the normal shock, we have a diverging section and a subsonic flow, so the Mach number reduces to 0.36 at the exit. If we look at the property ratios, we see they all decrease up to the upstream side of the normal shock. Then there's a sudden increase in temperature, density, and pressure across the normal shock. After the normal shock, we have subsonic flow, so the pressure, temperature, and density recover in the diverging section. Next, we'll go to the boundary between regimes 2 and 3. Now the normal shock is at the exit. We've reduced the back pressure, so the normal shock has got stronger and stronger and moved farther and farther downstream. At the boundary between regimes 2 and 3, it's at the exit. We have a maximum Mach number here. It looks like it's just over 2. And then there's a sudden decrease in Mach number across the shock. The Mach number at the exit downstream of the shock is 0.55. The property ratios all continue to decrease right to the exit, and then across the normal shock, there's that sudden increase in properties again. The pressure ratio for this condition is 0.5134. Now we're going to reduce the back pressure a little bit more, down to 0.5, and we move into regime 3. As I start to pull this pressure down a little bit further, we have a compression fan outside the nozzle. Notice the downstream or diverging section nozzle is purely supersonic with Mach 2.2 at the exit, which corresponds to the supersonic Mach number for an area ratio of 2. However, the pressure at the exit plane is much lower than the back pressure. As the gas exits out of the nozzle, it undergoes compression to match the back pressure. Therefore, we get a compression fan, which is a series of oblique shocks outside of the nozzle. We can continue to decrease this pressure further, and we notice PB decreasing, so the pressure increase that's necessary across these oblique shocks gets smaller, and the compression fan opens up and gets weaker. Eventually, we get to the boundary between regimes 3 and 4, where the back pressure matches the exit pressure, so the pressure just inside of the exit equals the back pressure. This is called the equilibrium condition of the nozzle. Again, the Mach number profile inside of the nozzle hasn't changed in regimes 3 and 4 because nothing that happens outside of the nozzle can affect what's going on in the nozzle when the back pressure is this low and we have supersonic flow in the diverging section. Now we go to regime 4 with a further reduction in back pressure, down to 0.07. Now we have an expansion fan outside of the nozzle, and we can go all the way down to a back pressure of 0. This has been a quick overview of compressible flow through a converging, diverging nozzle. The idea of this overview is to refresh your knowledge of these concepts. I hope it's been helpful to you. Thank you very much for watching.